Okay, so what I'll do is I'll essentially make a comparison between the two and then see how we can work with a spherical geometry along the same lines we developed in the Cartesian coordinates. And it's very, very different, much, much more complicated. And then I'll show you how you can obtain some approximate solutions, but approximate and accurate solutions for the three wave types we know, actually two wave types we know. Inertial gravity waves, also called Poincaré, right? Poincaré wave, we pronounce it Poincaré, I just want to make sure that. No. And then the other type is, sorry. Right, inertial gravity. Usually we refer to them as the inertial gravity, sometimes Poincaré. And the other wave type is the Rossby wave, or also called planetary waves, because they live on a planet in which the rotation, which the Coriolis frequency is not uniform. And then I'll maybe mention, it's not very pertinent for this audience, but the special types is the Kelvin waves, which we encountered in Cartesian coordinates, and it doesn't exist on a sphere per se as a degenerate wave in which V equal to 0, so only U and eta solve the shallow water equations, which is three-dimensional, so it's a very special type of solution, even though at very large K, all waves, all inertial gravity waves become actually gravity waves. And another type will be the MRG, called mixed Rossby gravity mode, which exists even on the equatorial beta plane. And I might say something about it at the end of the talk, just mention it, what the complexity with wave is. Okay, so just to lay out the problem, remember this was the first slide, one of the first slides in the Monday talk in Cartesian coordinates. We don't make this approximation. We don't want anymore the simplicity, the comfort, the ease of Cartesian coordinates. We want to dive right in to this real Earth. Earth is a sphere, and we'll do the work on Earth. And okay, just to remind you as a guide what we can expect, here's what we saw in the Cartesian coordinates. We have two inertial gravity wave groups, okay, one positive, one negative. They propagate, one propagating westward, one eastward. And then we have those vorticity waves, the Rossby waves, the planetary waves that propagate westward only. And we expect to encounter maybe a cousin of these waves on a sphere too. Yeah. Yeah. I don't mean you. I mean, no, the dispersion relation, if you want, I'll go over the entire slide. This is the dispersion relation of these waves. Right. It's not you. It's not advection. It's a Pythagorean summation of the inertial frequency and the gravity wave frequency. There is no you. East, just plain going east and west. One going eastward, one going westward. Along a latitude circle, yes. Divided by K. Divide this by K. It's omega, it's the frequency. So you divide it by K, you'll get the speed. The speed is omega over K. No. There is no advection. There is no advective, okay? U is 0, but you still get something that replaces you, which is the inertial frequency. I didn't say it, he said it. No, you say it. Oh, here on this. Well, if yeah, I said it about these waves, he said about these waves. The square root of GH is the speed of the characteristics, which is called the sound speed, if you will. But it's from a theory of PDEs, and in our simple mathematics, it's the speed that separates fast waves from low waves, a fast inertial gravity from low. No, not this sound speed. It's in PDEs. It's in PDEs. When you do the analogy, yeah, which we saw on Monday. It's terminology in mathematics to the speed at which, I don't know, maybe Jean-Pierre will be able to tell it in like 3 sentences, 3 words, because he doesn't speak much. It's right? It's moving. They change. Okay. I want to go into it. I thought you remembered all that from, this is Cartesian coordinates. This is classical textbook, actually drawn by Joe Pedlowski with his hands. With his hands, you see, he drew it by hand. So you see how this actually doesn't asymptote where it's supposed to be asymptotic, but that's the artistic properties of Joe and his wife, former wife is not one, deceased wife is not next to him. His wife was an artist, but he was not, as you can tell. In any event, we know this, and what we want to do is we want to start by doing a comparison. So we'll write now together or side by side the planar or the equations we had on the, the equations we had on the beta plane, with which we worked for the last 3 days, or the Monday, Tuesday, and Wednesday. And here is the same equations, but in spherical geometry. So in spherical coordinates, what you see is the Coriolis frequencies sine phi, approximated here by this linear dependence on the beta plane. And also here, this is sine phi, this is its linear expansion about some latitude, which defines the y equals 0. That's where we set y equals 0. And this is the beta plane approximation when you expand sine phi about a certain phi 0. And what you see here is that we took the cosine phi to be constant here and here and here. Okay? So what happens is we expand in the beta plane approximation, we expand the sine phi to first order about phi 0, but leave these terms, cosine phi here, and cosine phi there, at order 0, okay, which makes the approximation inconsistent, at least until you show that it can be done. Okay, we leave this to be cosine phi 0, so a cosine phi 0 times d lambda is exactly dx. That's exactly the definition if you look at what happens along a circle. And the same thing is true, of course, here and here. We just take cosine phi 0 to be 1. Okay, so this is the beta plane. So what we do to both of them, and again, you read 1,000 pages of Pedlowski, that's maybe 999 pages are in this setup. And you read Vallis, it's again the same thing. So we do, again, the same thing to both systems. What do? We assume a propagating wave solutions in the horizontal or along a latitude circle or along y equals constant. In x and t, there are no x and t coefficients here, so we can use the separate. We can assume by Fourier decomposition e to the I kx times e to the I omega t minus omega t in x and y, and here e to the I k lambda minus, or e times e to the minus I kc t. Okay? And then again here, as we said on Monday, here there is no y or phi derivative. Therefore, it becomes a linear equation that relates u, v, and eta after you substitute these expressions, these wave expressions. And then you take this u you get from here and substitute it here and here, and you get the system too. So if the initial template is exactly the same, okay? And we can easily do it. Okay? I mean, all of them. U, V, and eta, all of them are in one wave solutions. Oh, everything depends on U, V, and eta, but with a y-dependent amplitude that will be different, or phi-dependent amplitude that will be different for each one, U, V, and eta. Same K and same omega. Okay. So, and then actually we get a second order system. Okay, so again, in either of them you can get the second, here it is, okay, the second order systems in both geometries. And again, this one we worked on for a while. What we did was to transform it into a Schrödinger equation by eliminating one of them. So we're transforming a system 2 into a second order differential equation, and that template works in both cases. But of course, there are many, many more phi-dependent coefficients here than y-dependent coefficients there, and therefore the equations are going to be very, very messy. So bear with me, I'll try to navigate through it without glitching into potholes. Okay, so just to let you know, numerically they are equivalent, entirely equivalent. There's absolutely no problem in solving one versus the other. And in order to reduce the number of parameters, we scale them, and we scale them here such that the radius of Earth is the velocity scale, 2 omega is the velocity scale, and length in these coordinates is x and y are determined on A, and eta is on H, and t is a 1 over 2 omega. I think we did the same thing before. And the point that has to be stressed even now, I mean, as early as now, is that while here in this system, in Cartesian coordinates, it makes sense to eliminate eta and obtain a second order equation for V, because in order to close the differential problem, we have to impose boundary conditions. And the boundary conditions, again, on the mid-latitude beta plane, are the vanishing of V at the two walls. And therefore, it makes sense here to derive the second order equation for V by eliminating eta. This is not the situation here. This is a sphere. So there's no channel, it's an entire sphere. And the boundary conditions are only regularity at the poles. And the poles, as you see, are singular points of these equations. So these are the boundary conditions. Boundary conditions at the singular point, the solution has to be regular. That's a perfectly legitimate boundary condition. But on a sphere, we can either eliminate V or eliminate eta, because both of them have to be regular at the poles. We don't want a solution that explodes at the pole. Okay? So the freedom we have here, despite its massive complexity, is that we can derive two second order equations instead of one, which makes sense to derive here. Okay, so let's continue. I'm not the first one to attack this problem or to study this problem. This problem was studied in the 1960s by Longit-Higgins in a very, very fundamental book, which I believe hundreds of people cited, but very few read from cover to cover. Allow me to speculate. I did, but it's like 100-page long. It's really not a paper. It's like a booklet, and it's filled with tables, and it's a very thorough analysis of this system. Okay, so he wrote it all as if it's an eigenvalue problem. This epsilon, and you will see that epsilon repeating in my analysis, even though I used alpha before. This epsilon is called the Lamb parameter, and it's just the opposite of GH over 2 omega A squared that we used before. Beforehand, in the Cartesian coordinates, I used alpha, which is just the normalized speed of gravity waves. But here, in order to be consistent with Longit-Higgins, I took this epsilon, you just scale the equations a little differently, and you get the same thing. Oh, wait. Right. His notation needs to be clarified from the beginning. Okay, so his S is my K. Okay, his lambda is my omega. Don't ask, yeah, his lambda is my omega. So lambda is, today to call lambda frequency is out. So KC is the omega. K times C is the omega. But allow me to skip this. I think also his theta is, if I remember correctly, is the, I think it's the co-latitude. I think he uses the co-latitude. He uses the co-latitude. In short, you see his singularity here is when theta is pi over 2, when theta is 0, which is the mathematical way. I told you on Monday, the mathematicians prefer the co-latitude, 0 to pi. And we prefer minus pi over 2 to pi. So it's pi over 2 minus pi or something like that, pi minus pi over 2. In any event, I'm not going to go through his analysis, but what I want to show you is that his eigenvalue problem is very upside down. Mathematically, it's an eigenvalue problem. You have a linear operator, okay, and you ask what are the eigenvalues, which is a question. But for wave dynamics on a sphere, what we want to know is the dispersion relation. So we want to know how the frequency depends on the wave number. But if you go through frequency and wave number, we want to know here to know the functional dependence of lambda on S. But you cannot solve this equation without specifying lambda and S, from which you determine this parameter, which for us is a parameter. You don't have to evaluate it, okay? So it's an eigenvalue problem, but I would say it's the wrong one, okay? You assume you know the wave number and frequency, and you ask yourself, so what's Lamb parameter? What's the speed of gravity wave? And maybe you'll get it, okay? But it's really not what will help us obtain dispersion relations for the waves in GFD. A few more words, okay, lambda is the frequency, theta is the co-latitude. Hey, at least we are consistent. Latitude plus pi over 2, this is the, and S is the zonal wave number, what we usually call K. And this is I don't want to say ugly looking equation because mathematicians jump on it because it's very interesting. There is a lot to work, but it's horrific. Okay, it's very, very unpleasant to work with. Even if you could solve it somehow, you won't get lambda of S, the dispersion relation that we are after. We want to know what lambda as a function of S is. Okay, so a few more words about this equation. The paper, or about Longit-Higgins's work, it has like, it's an encyclopedia. It like has 31 figures, each figure with maybe between 10 and 20 graphs, and it has 10 tables, you know, that tell you it's almost impossible, you know, page-long tables, and numerically calculated solutions of the. In any event, he derives analytic solutions. Not all 97 pages are just tables and figures, and in the text he derives some analytic solutions. And the analytic solutions are derived for two cases. One is very near the equator when his theta is pi over 2, our phi is 0, in which case he get it, but he certainly didn't know, he get expressions, but it's obvious that he didn't know when he wrote the booklet of Matsuno's work, which was published 2 years earlier, but in Japan. And remember, this is the era where reprints were shipped by ships, literally by ships, okay? And by the time the library got these, it was way more than just months. He didn't read Matsuno's work, so they are in error. It can be forgiven because Matsuno's work is all analytical. He did it with, and this one is, along with Higgins, spent a lot of, I'm not sure you call it computation, 60, they were hard computers, right? Very, you know, beginning of the era of computers. In any event, he did his best, and it's very impressive what he did, amazingly impressive. But somehow when you compare it to Matsuno, you see that there are differences. There are also another limit in which he has analytic expressions, and that is in the non-rotating case, where this, when this epsilon goes to 0. So for 0 epsilon, he has some analytical solutions, but Earth is a very fast rotation. So in terms of this lamp parameter on Earth, it's large. It's much larger than 1. I don't say it goes to infinity, but it's very large. Okay, what else did I have there? Okay, this is it. So let's go back to the equations. This is their form in just in case you don't remember what I said on Monday. Arthur wasn't here on Monday. This is the shallow water equations in vectorial form. There are no coordinates in here, and V is the two-dimensional field, and G is the gravitational acceleration, eta is the deviation from H, K is the unit vector in the radial direction in our case, okay, go out of the sphere. And if you write it in Cartesian coordinates, okay, I'll write it in I think we had it before, the Cartesian coordinates, but the way we want to get to, okay, I'll show you in a minute some intermediate ways, some of the intermediate ways, but what we really want to get is something that will look something like this. You'll have the second derivative, and you'll have terms that will be the spherical counterpart of what we know worked so well in planar geometry. Okay, so we have the solutions on a plane, or the form of the Schrödinger equation on a plane, and we say, this k goes here, this is omega goes here, this is, here cos phi, of course, we don't know. So we can have sort of laws of translation between the beta plane and the sphere, and we'll call this, which is phi dependent, these terms, we'll call them the potential, and these we'll throw away because they're multiplied by this. Remember, alpha is 1 over epsilon, and this is going to be our energy, again, keeping the cubic relation between the energy and the phase speed. So once again, for each, if we solve it, when we solve it, hopefully we solve it, we get E as the eigenvalue, and each E gives us 3 C's. And we know how to identify the large and 2 large roots of the cubic equation will be Poincare waves, and the small negative one will be Rossby wave. So if you write it as a matrix, this is what you get. Okay? Again, scaling, which is sort of unimportant, but here I adopted the alpha scaling that gives us alpha. And from it, we can eliminate U, as I said before. And by eliminating U, you get this matrix. And this is a 2x2 system that actually, had we known how to solve it as an eigenvalue problem, there would have been no continuation, but we don't know. So the only thing we can do is transform it into a second order equation, and that's where all the mess begins. And from that point, we can try and develop those laws of transformation, okay, from the planar system to the spherical system. And what we realized is that on the beta plane you have k multiplying x. This k should be transformed to x over cosine phi on a sphere, because on a sphere lambda replaces x. So you now have to pay for it with the appropriate transformation of k. The phase speed does the same transformation from c to cosine phi. By the way, when you multiply them, of course, you get omega, and omega doesn't know whether you're working on spherical geometry or planar. And the Coriolis obviously goes from something that's linear with y, it goes straight to, sine phi. And the variable that goes in here, it's just a lot easier to write it this way, to put the cosine phi here, in which case this is the way the matrix looks, okay? So we have a matrix, the counterpart of this matrix is this one, and you see the omega squared didn't change. This one became here. Here you have cosine phi because c is replaced by cosine phi. This c is replaced by cosine phi. This c is replaced by c cos phi, etc., etc. So these are the rules of transformation, okay, from plane to a sphere. So once we know that, we can go back to this equation and say, we will define, I'm now eliminating eta, okay? We'll define V to be psi times this, in which case we get this horrific equation, okay? Since Longet-Higgins got a horrific second order equation, it's no wonder we also get a very, excuse me, if I may words, ugly looking equation. So this is the ugly looking equation that we get, which is the counterpart of Longet-Higgins. And notice that I put them on two separate lines. This line, by the rules of transformation, are exactly the E that we had, or the terms we had on a plane. What did we have? We had something that went as 1 over c. Now we're getting omega squared, which you multiply the whole thing by alpha, and it'll be here. And then k squared that goes into cosine squared, and then sine squared, which was f squared in our case. So these four terms we encountered in Cartesian coordinates. All these are essentially the spherical complication of the aforementioned simple equation, okay? So we'll write the equation as something like that. This is the equation we want, okay? Call this E, the two constants we'll call E, the energy, and we look at this equation. Remember what I showed you, where we're heading. So we are heading to solve this equation. Again, if you multiply the alpha, you get the alpha here. And this is the equation we'll work with. Oops. Okay, and just remember that we neglected all those terms. If I multiply by this epsilon, say again? Right. Correct. Correct. Absolutely correct. But remember, here I multiplied by alpha. So this term, so these terms now will be multiplied by alpha. Okay, so if you ask me what's the residue here, what do I miss here? I miss alpha times something. Okay, this notation, just because I multiplied by alpha. So all the spherical terms that I am dropping are multiplied by alpha, which is a great help if alpha is small. Okay, so what can I say about it? Boundary conditions are regularity at the pole. E, of course, in this problem will give us 3 C's as before. Here is the cubic equation. It becomes much simpler, or a little simpler perhaps. Okay, but you have to know E from this equation. And I'm just saying it, I'm not going to do it, but you can do the same thing and eliminate eta. And if you do the same thing, and I'll show the result later on, but you can do the same thing, eliminate V and get an equation for eta. And notice that the singularity of these terms occurs, not singular, singular latitudes occur when C squared is less than this alpha. In the other equation, it occurs at different places, in different, at different latitudes. Singularity of these neglected terms. Okay, so just an outline of what I'm going to do now. What I'm going to do now is I'm going to approximate I'm going to write the potential as U1, which is the one I showed you. Oh, sorry, let's go back. Okay, so this is going to be our U1. This is U1. What I neglected is going to be alpha U2. Okay, and I'm going to, this is the full potential, including the spherical terms. And I'm going to concentrate on U1 only, or neglect alpha U2. And the terms there are sine squared and cosine squared, so they are symmetric about positive and negative phi, so I can expand it in phi. And if I expand it in phi, you get an equation, something like this. Okay? The cosine becomes 1, and this is the expansion in phi of this U1. So there is an expansion of this potential in power series in phi, and we retain the phi squared term and get a Hermitic function or Hermitic equation, and we can solve analytically and get the En explicit expressions for the energies of the Schrödinger equation. And of course, we get 3 C's, and we know 2 large and 1 small. So this is the template of comparing analytical solutions based on this approximation with the exact analytical numerical solutions of the 2x2 system or 3x3 system. So let's see how it works. So first of all, this is just you take 2 numbers for K and C, and you plot the potentials, and you see the following. This, the dashed line, is the exact potential, U1 plus alpha U2. Okay, here it is. This light blue one is the approximate solution U1, and you see that U1 agrees with the full solution up to maybe very close to the poles. At the poles, there are, of course, some differences. And the red line, the red curve, is the parabolic approximation of U1, of the approximate potential. So there is a parabolic approximation to the approximate potential. And if you now go and do the eigenvalue problem, you find out that I can fit, or not I, but the equation fits about 60 energy levels at a range of about, say, less than 0.4 in terms of phi. So at the latitude of 4 pi radians, which is less than 30 degrees latitude, you already have 60 energy levels, which means that the approximate solution we will show in a minute, will be relevant for the full solution, for 60 waves or so. If you go now to 10 to the minus 4, alpha of 10 to the minus 4, then again, the purple, the blue, light blue, and the dashed curve agree again to very close to the equator. And the red one, of course, the phi squared approximation, Okay, this approximation works only very close to phi, to the equator. And if you look at the eigenvalues, again with this case, you can see the problem. The problem is now we can get only an order 10, maybe less than 10, energy levels before all potentials diverge. And this is alpha of 10 to the minus 4. If you go now to 10 to the minus 2, okay, this is that, then you see that the problem is even more serious because this began to diverge from these two at a very low, relatively low latitude, but you can fit in that latitude only maybe 2 waves or so. The third one will probably be already in error. So only a few number of waves. But if you look at the dispersion curves, they look pretty well. You know, okay, you see the dots are the numerical values and the straight lines are the expressions I showed you before. And the agreement is very good. 10 to the minus 6 is even better. And, oops, wait a sec. This is 10 to the minus 4. 10 to the minus 6 are very good. And 10 to the minus 2, we know it's not going to work. And if you look at the eigenfunctions, again, the same thing. You see this is exact and one is the Hermite. The blue is the exact and the red is the Hermite function. And you see how well it is approximated by the Hermite solution. You go to n of 1, again, perfect agreement. You go to n of, 5, and you see again it agrees very well. And of course, you can go on and compute, but it's not going to last forever. So both the eigenfunctions and the eigenvalues are in excellent agreement with the numerical solutions. So I want to make 3 remarks and then move on. The results I show you depend on, of course, both K and alpha. They're just examples of what I showed you. But for very large value of K, they work well even when alpha is 0.2. 10 to the minus 2. 10 to the minus 2, sorry. Okay? But K of 100 is a bit unphysical for the world. The second thing I want to say is that, yeah, K of 100 is not really an interesting wave number. And the accuracy of the alpha less than 1, much less than 1 theory is limited not by the neglect of alpha U2, but by the approximation of U1, the approximate potential by phi squared. So had we known how to solve the U1 the Schrödinger equation with the U1 potential of sine squared plus something over cosine squared, then we would have been doing much better, but we don't. We only know how to solve it for a parabola. Okay, so it seems like the U1 itself, the Schrödinger equation with U1, not with the phi squared, is relevant even for alpha that is relatively large, what we call barotropic. Just to show you, here's an alpha of 0.05. And if I take now and solve the 2 equations, one of them yields me E, the approximate one with U1, again, numerically. And one of them, the exact one, gives me K squared C squared minus alpha over C. You see that they line very nicely on the Y equals X, or K squared K squared C squared minus alpha over C equals E. So, and this is for large value of alpha, and this is for about 100 modes. N goes from 0 to 9, N goes from 0 to 9, and K goes from 1 to 10, so it's about, 10 by 10, yeah. Correct. The first 10, yeah. As I said, no one looks at wave number 10. I think wave number 10 along the equator may be somehow relevant to something. The solution is not harmonic. Make it a parabola. Yeah. Okay, so all I'm saying is that the U1, a numerical neglect of alpha U2 is not terrible. It doesn't produce any error. Okay, just a few more examples. You see, this is alpha of 0.05, and again, the numerics works very well. No need, you see, this is large K. You can go into regular dispersion relation as we know it. Omega is a function of K for various n's. And again, you see that except for here, we get an okay agreement. Maybe I should say that. Okay, so what I would like to, last part of this talk is to say small alpha and perhaps large K are also can be somehow addressed. But the question is, can we do something better by resorting to the eta equation? Remember, we're exploiting at this point only the V equation, eliminating eta from the second order system. So if you look at the second order system, we can eliminate either of them. We don't have to eliminate eta, we can eliminate V and obtain a second order equation for eta. So I don't want to go again into the whole thing, just to show you what we can get by comparing the two. It gives us a very interesting classification of the modes, not only approximate expressions that work very well for these or those, those are particular values of the wave numbers. So here is the equation again. I reverted here to epsilon here, but epsilon is just 1 over alpha. And what I would like to say is that when in this limit, okay, for large omega, but omega larger than epsilon, then we can in principle replace this by a concept. We don't have a singularity here. So what we will want to do is eliminate this term. So this is done by, can be done in one way. On the other hand, when omega is smaller, this time it is smaller than K squared, then this term, okay, will never vanish. So remember, our problem was the vanishing of those terms in the U2 potential. If you want to avoid it, then what we can do is we can do now the trick of going from V to eta, in which case we'll get a different singularity in each of the systems. So we can get Schrödinger equations for eta in one hand, in one limit, and Schrödinger equation for V in another one. And it turns out that if you put K equals 0, you also get a Schrödinger equation. So basically we have 3 Schrödinger equations that we can play with or work with in order to get a more complete solution of the mapping, if you will, of the solutions of this equation. It's something that depends on phi, okay, varies north-south, oscillates with time, and it is uniform over the entire globe. Uniform, yeah. Correct. Doesn't vary with x. So not steady.
I understand.
Right. Oscillates in time and has a certain structure in phi, in latitude. Okay, so so we can now look at various limits, and I'll save you the time because I think I'm exhausting your patience. But if you map now the omega k plane, you can find several interesting regions. The first one, number 1, is where we have no approximate Schrödinger equation. Here there are no, and notice this is exactly the region in which there are no solutions. We don't have waves there. As I showed you in the first slide, this is the area where we don't have Rossby waves and we don't have inertial gravity waves. Then we have region 2. Region 2 is the omega squared much less than k squared, okay? So it's here. And in this region, we have the V equation, which gives us Rossby waves, or this is the area where Rossby waves have their dispersion relation. Area 3, okay, here and there, is k squared, omega squared that's larger than alpha, and you get an eta equation, which gives us the inertial gravity waves. It's here and here. Okay? And in region 4, we have no solution here. No, oops. Region 4 here is, we get two contradictory, if you will, Schrödinger equations. And there is another interesting solution, the k equals 0, aforementioned, which has a solution only when one Schrödinger, along k equals 0, we have a solution, I'm sorry. And we have an omega minus k solution, seemingly like an anti-Kelvin, but this has a regular solution only for a particular value of k. Okay, so there is one point at which a solution is allowed to cross this line. And this gives rise to the mixed gravity mode, inertial gravity mode. So to go in a little zoom in on this region, this is for epsilon of 16, so the square root of it, the fourth root of it is 2. What you see here is, again, this is region, I think it was 3? No, 2. Okay? And what you see is that indeed you have Rossby waves, and the Rossby wave here terminates, giving rise to a Poincare wave. This is a blow up of this region. In the rest of the region, you have lots of inertial gravity waves. This is where things begin to be a little messy, but you see that this blue line can cross it in one particular case. At one particular point, this is the omega equals minus k curve. If you do the same thing for omega, for epsilon of 10 to the 4th, so that the fourth root of that is 10, then you get a similar picture. You see you have here the Rossby waves, and here you have the n equals 0 Rossby wave that crosses the omega minus k at that k squared and continues as, if you will, as an inertial gravity wave. So this gives rise, if you will, the crossing of the omega minus k curve at one point gives rise to the mixed Rossby gravity mode that is actually n equals 0 Rossby mode for sufficiently large k, and the n equals 0 inertial gravity mode at small k. And you see it here crossing very nicely. I zoom in on the region of, the eigenfunction first. You see that it moves from one region, as far as the eigenfunction is concerned, it moves from one region where we don't have a solution to a region where we have more than that, then it moves smoothly, and the behavior of the eigenfunction is easy or smooth across those domains. You can also see it here in large epsilon, where you have a wider range of k's that are occupied in the no-fly or no solution zone, no Schrödinger zone, but numerically, it just goes smoothly from one to the other. Just our knowledge cannot comprehend that. Okay, so a little zoom in on this region where it crosses, show you that it's a very delicate transition that somehow, I can't say I understand exactly how Matsuno found it in Cartesian coordinates, but he was smart enough to do it analytically on the beta plane, the equatorial beta plane. You see he's the first one to call it the mixed Rossby gravity mode. And you see here on the sphere, it's very hard to see what's going on. You really need to go carefully into it. The other ones, of course, go straight in it. But the n = 0 is the mode that crosses the omega minus k and doesn't go up as a Rossby wave, or if you will, begins as an inertial gravity mode, but then crosses where all other cannot cross, therefore they bend downwards. Well, I think this is what I wanted to show you. So it's the basic mode, fundamental mode. You mean whether there is? I think I showed you, no? It's the eigenfunction. Yeah, this is it. N = 0, meaning there is no zero crossing. But you see here I have a Schrödinger equation. So I can tell you n obeys the rules of Schrödinger equation. In other words, the mode number counts the number of zeros of the eigenfunctions. Here I don't have a Schrödinger equation, so I cannot claim that, but it is so. And here too I have Schrödinger equations, and it does, perhaps different. The eigenfunction. It's phi. It's eta. It's eight. In all of them, I think it's eta. No, it's v. Sorry, it's v. It's the same function plotted in all these panels. Okay, and the amplitude, of course, it doesn't matter because it's a linear problem. So they all normalize such that the maximum is 1. And you see, this goes easy, even those here, there are some differences, numerical differences, but not analytical. Okay, I think that's what I wanted to show you, the MRG mode, which on a sphere, I think you can more easily understand what's going on. And just to conclude, I think what I told you was that the accurate, for small values of this alpha, we can get accurate expressions. Rossby and Poincare waves are derived from one eigenvalue problem as it was on the plane. They vanish for small alpha, the eigenfunction vanishes at finite distance from the equator. Perhaps that's why the planar approximation of Matsuno's work works so well. And in a barotropic, we have to do some more careful work of doing both V and eta, working more carefully with V and eta, and derive a complete set of approximations. And perhaps it's not going to be shocking to you, but to our community, it is. Kelvin waves as a separate wave type do not exist on a sphere. Separate in the sense, see? You are the only one who raises his hands. How can it be? Yeah, I understand. I understand. Yeah. Yes, but how do you know it's Kelvin? Yeah, but that's precisely the issue. Yeah, it's an inertial gravity wave. It's an inertial gravity wave, but it's very low order in terms of n. Therefore, its phase width is very similar, or maybe almost identical to that of a Kelvin wave. Okay. Its structure, as you saw, is a Gaussian, which is what we know from Kelvin wave, but that's not a Kelvin wave what I showed you. Okay, so on a sphere, you start counting the normal wave. On a plane, you have another solution, which is very degenerate, in which you have V = 0. Okay, V = 0, and U and eta satisfying 3 equations. They satisfy 3. You have 3. You start out with 3 equations. So if v is identically 0, you have two functions that satisfy three equations. That's very unusual. It doesn't happen on a sphere. So what comes instead of it is that the n equals 0 Poincare mode is very much the counterpart of the k Kelvin on a sphere, and you have to shift all others by one. So maybe to repeat some of what Arthur said yesterday, this is a quote from Isaac Newton. To myself, I am only a boy playing on the seashore, whilst the great ocean of truth lie undiscovered before me. So thank you.